today's video, we're actually going to jump ahead to Chapter 8 and switch gears a little bit and take a look at radicals along with exponents. If you take a look at the three examples that I have listed here in front of you, we have square root of 16, square root of 64, and cube root of 8. Now, we should hopefully all kind of know what those are. Square root of 16 equals 4. Square root of 64 equals 8. And the cube root of 8 is 2. Now, a couple of things I just want to quickly review with you about. Right here, you have your radical, and that refers to the actual sign right there. And inside there is an index. Now, if no number is listed, it's implied that it's a 2. So the index of a square root is 2, where the index of a cube root is 3. Then right here, the number inside is called a radicand. And basically what this kind of tells you is that I'm looking for a pair of numbers that are the same that will give me 16. So the 2 refers to a pair, which would be 2, whereas a cube root over here says I'm looking for 3 numbers that are the same that multiply by 8, and that's where that 2 comes in. Take a look real quick at the cube root of 8. I can rewrite that as 2 cubed. And basically what happens is the cube root cancels the cube, and that's where the 2 comes into play. And the reason that is because the index is really like a fraction in your exponent. It's rational exponent. So this right here is 2 to the third, while the radical actually becomes 1/3. And then by the property of exponent to exponent, you're multiplying those out. So if I go back to this middle example, the square root of 64, there's an imaginary 1 right there, is really 64 to the 1/2 power. The exponent of the 64 becomes the numerator, while the denominator comes from the index. Therefore, this is kind of where that property comes in. You can write a fractional exponent as a radical. We're going to be taking a look at quite a few quick examples of how you evaluate using these and how you can simplify them. So if we look at number 1, it says 32 to the 1/5 power. And basically what that means is it means you have 32 to the first, and it's the 5th root. Basically meaning what number times itself 5 times will give you 32. That would be 2. Because if I did 2 to the 5th, that would give you 32. The 5 and the 5 cancel because of the property of 5/5, which is 2 to the first. Now in the next one, we have negative 81 to the 1/4. Now because the negative is outside the 81, the 1/4 only applies to the 81. So it's the 4th root of 81 to the 1st power. So what number times itself 4 times gives us 81? Well, that would be 3 to the 4th power, which would be 3 to the 4/4, which just gives us 3. But because there's that negative sign, it's actually going to be -3 is our answer. Example number 3, we have 25 to the 3/2 power. And what we're going to do here is we're going to start out by writing this as a radical. So we'll have 25 to the third, or the square root of 25 raised to the third power. Now you can actually manipulate this a little bit, and you can kind of rearrange this and just take the square root of 25 and then raise that to the third power. It's kind of, you can kind of switch it up and evaluate it individually. The square root of 25 becomes 5, and then I can raise that to the third. That becomes 125. We'll do the same thing with number 4. I'm going to do the cube root of negative 64 raised to the second power. Again, taking 64 and squaring it, that's going to give us a very large number, which would be hard to work with. So what we'll do is we'll take the cube root of negative 64, and we'll square that. The cube root of negative 64 is negative 4, and if I square that quantity, that's going to give me 16. In these next two examples, I just want to point out a couple of special things that you might not catch. Number 5, I want you to notice the difference of the placement of the parentheses. Over here, the 3/5 just applies to the x, where in the second term, the 3/5 applies to the entire quantity 2x. So when I go to write this first one, it's going to be 5 times the 5th root of x cubed minus the 5th root of 2x cubed. And we'll go ahead and cube the 2x. And because these aren't exactly the same, they have to stay separate, so that's going to be our final answer. In example 6, we have x to the negative 5/7. And what you just need to make sure you remember when you're doing these is negative exponents. Remember, those get moved down to the denominator, so 1 over x to the 5/7. And then I create it as the radical. 1 over the 7th root of x to the 5th. We're not going to go over number 7 fully, but I do just want to point out, just like in the last, in question number 5, just notice where the parentheses is at. In this case, it's just for the 5th root of x, where here it's over 2x completely. But let's take a look at number 8. We have the square root of 9 to the 8th. Again, trying to do 9 to the 8th power would get very large and take a lot of time. I know you have calculators, but this is actually a problem that's easy to do with pen and paper. I write this as 9 to the 8 over 2 power. That reduces to 9 to the 4th. Sorry, this should actually be the 4th root of 9 to the 8th. So then it becomes 8 over 4, which becomes 9 squared, which would be just simply 81. Again, 9 to the 8th would be an extremely large number, but because those two are divisible to each other and give you a pretty easy exponent to work with, it's much easier just to do it with pen and paper or mentally. And we can use rational exponents in just the same ways we did in the previous chapters. If I have exponents to exponents, they multiply, so it'll be a to negative 3/2 times b to the positive second, because I'm going to multiply the exponents together. And then I'm going to get a to the first, and then b to the negative 1/10. From there, because I just want positive exponents, I'm just going to move those around. I move the b to the top and that a to the denominator. and then I'll just go ahead and add those together. So it will be b, and if I have a common denominator, that will be 21/10, and then in the denominator I will get a to the 5/2. And the same with number 10. When I distribute the r to the 2/5, when you distribute, remember that you are multiplying, so you're actually adding the exponents. So 2/5 plus 3/5, that's going to give you 5/5, which is be 1. And then when I go to distribute to the next one, I have r to the 2/5 plus 8/5, that's 10/5, which will be r to the 2nd. And finally, our last two examples, simplifying with radicals. What I can do, because we haven't talked much about multiplying radicals with different indexes, what you can do is you can just change these to exponents. X to the 3/4, x to the 1/5. From there, what you need to do with those exponents is simply add them together. So I'm going to do a common denominator, which will be 20. So this will be 15/20 and 4/20, which gives me x to the 19/20. So I can actually add those together. And finally, I have a radical within a radical. So what I'm going to do is I'm going to change that first one in there to x to the 1/6. And then I'm going to change the outside radical to a fraction as well, to the 1/3. And so it becomes an exponent to an exponent, which can simplify down to x to the 1/18. So again, it's just a lot of little properties that we've learned in the last chapter and kind of how we apply them.